Okay, yes, the seminar started. Today we have Dr. Shen from San Anthony Fall Laboratory. Dr. Shen received his undergraduate degree in modern mechanics at the Department of Modern Mechanics at the University of Science and Technology in China in 1993, and he received his PhD in fluid mechanics from MIT. He's currently a professor in the Department of Mechanical Engineering at the University of Minnesota, and as I mentioned, he's the director of the San Anthony Falls Laboratory. His research interests include computational fluid dynamics, water waves, turbulence in the ocean, and lake environments, and offshore renewable energy. I think you'll be treated with a lot of discussion about the use of computational methods, computational fluid dynamics, in the study of environmental issues as well as geotechnical issues.
Thank you. Well, it's a pleasure to be here to give a talk, and actually probably it's my first time in this building. It's really nice. Yeah. And yeah, also yeah, I guess I need to stand in front of the camera. So yeah, so hi. So I'm going to talk about our study on geophysical flows and the environmental flows, and at the San Anthony Falls Laboratory. So before I start, I want to give a quick introduction about the lab. Oh, great. Okay. Yeah. So San Anthony Falls Laboratory, which we call the SAFL, is the lab just by the waterfall, and its location is really nice. But it's not mainly for the view. The purpose of building a lab here is to utilize this 50 feet of waterhead. Okay. So basically, it is built by this reservoir, and then when the lab people needed to do experiments, then they actually predictably let this river water to run through this lab, okay, and eventually return to the lab. So therefore, a lot of facilities in the lab, okay, it has many different channels and flumes and so on and so forth. Okay. They all utilize the water from the river and eventually return to the river. Okay. And it has almost 80 years of history. And actually later this year, we are going to have quite some celebration about this 80th birthday of the lab. Okay. And the research in this lab, okay, when it was established, then that is mainly for hydraulics. Okay. Then as time went on, okay, then the research focused into different areas depending on which stage. Okay. And in the past decade or so, okay, then it is mostly focused on fluid flows, okay, in natural environment, in the energy, mostly renewable energy applications, and also there are some biology and health applications. And the lab has been the home of some big national research initiatives. For example, MSAT, that is a bigger NSF center, that was headquartered in the lab. And also it has been quite active in wind energy research. And at this moment, it has 21 affiliated faculty members come from 5 different departments and 2 colleges at the U. And also it is quite unique. It's for the lab. It has quite some, actually here, 37 research staffs, including research associates, postdocs, and also administrative staffs and IT person. And also we have a large engineer team. Okay. So they carry quite some applied work. So the lab, okay, has quite some facilities, as I mentioned, okay, and it has a lot of rooms and model basins, and so it can mimic like deltas and earth surface processes. Okay, and here is the wind tunnel, okay, and here is those wind turbine, okay, models. Okay, and actually we also have the real scale, okay, that is utility scale wind turbine, but that is located outside, that is in that Rosemont. Okay, and here, okay, it has 2.5 megawatts, and here looks it's not tall, but actually it is 80 meters then this metal tower is 130 meters. And then, okay, so, well, 80 meters is really high, okay. So when I first took over the job, the first thing I did is I went there and I climbed up to the wind turbine, okay. And it took me almost 2 hours. Yeah. Yeah, okay, so when I was on top of that, then looking down, that those cars are really small. Yeah, okay, yeah. So, so there are quite some facilities, okay. But most importantly is the lab has a lot of nerds. Okay, that is what we are proud of. Okay. And several years ago, the lab went through quite some renovation, okay, because the building, after all, that is like 70-something years old building, okay. And after renovation, and then okay, we started to have elevator again, okay, and we had air conditioning and so on so forth, okay. So now, okay, the lab is in quite a good shape, okay. So if you haven't been there, okay, or if you were there quite some time ago, you are very, very welcome to go there to take a look at this lab. So the lab research is centered around a lot of flows, as I mentioned earlier, happening in the natural environment. So for example, okay, like here, okay, well, here's about the restoration of deltas, rivers, and the lake environment, okay, delta, and then okay, about the water quality, okay, and about relating to human health, okay, and then okay, renewable energies, basically wind energy and the marine hydrokinetic energy, okay, and the turbines and so on and so forth, okay. And then okay, also, for example, to study the impact of climate change on lake environment and so on. And for example, okay, about hydropower, okay, then okay, here's one facility that is our biggest channel. It has about 84 meters long, okay, and then okay, for this one really, okay, this is the river water, okay, and then when we need to experiment, okay, then we just let the water going through this big channel. And also we can do quite some physical modeling, okay. So yeah, as a matter of fact, okay, when the lab was first built, then in the 1940s, 50s, around that time, around the world there were many like big dams, reservoirs built. A lot of those models were first tested in the lab. Okay. And so, okay, and here is a high-speed wind tunnel, okay, and then just like wind tunnel, but what is wrong here is the Waterway, is water medium. And on natural environment, for example, we are looking at this waterway restoration, okay. And so we can study that both, okay, in the lab, and this one is called outdoor stream lab, okay. So that is outside of this building, and use this unused spillway, okay, to build this, okay, to mimic the meandering of a river stream system, okay. And so that is outdoor, but meanwhile it really has the quality of indoor, okay, lab experiment. Okay, so it is heavily instrumented for that. Okay. And then, okay, we can arrange, here different stones, and you can see, okay, and then to study how flow goes, okay, around here. Well, having said that, okay, next I'm going to focus on the research in my group, okay. And one funny thing is, Symphony Falls Lab is essentially a big lab facility, okay, and it has, as I mentioned, 25 faculty affiliated faculty members, 37, staff members, and who knows how many students, okay, yeah. But I always joke that among those people, I'm the only one in the lab who does not know how to do experiment. Okay, yeah, because my research tool has been using computer simulations exclusively. Okay, and so these are my facility. Okay, and for some of them, and most of them, actually, I have never seen them myself. Okay, and this one, well, okay, is a cluster computer, parallel computer, owned by the lab, and this one is MSI computer. Okay? And this tool belongs to the DOD. Okay, and actually we use the largest DOD supercomputers for unclassified work. Okay, and so basically we use computer simulations to mimic the flows, okay, in different environments and tend to study their behavior. Okay? And so to give an example, okay, like here, okay, are the set of tools developed in my group, okay, to study different flow systems happening mostly in the nature. So here is how we do the surface waves happening at the ocean surface and lake surface, okay. And this is not like animations or not some from movie. This is done based on the computer simulations. Okay. So therefore, we are able to simulate the wave flows in a very realistic setting over a large domain. Okay. And then based on that, we can study, for example, how wind blows over wave surface. Then that we can use that to study the lower atmospheric. And then for the upper oceans, upper lakes, then to see what's the process going on there. And this one is some quite interesting setting, that is what happens near the coast. Okay. Then we have the interplay between the air flows and water flows and also land surface processes. Okay. And then those are for engineering applications, okay. And those are all for small scales like wave breaking and bubbles and here sprays. So for those things, okay, I can go on to show some more detailed example. Okay. So here is the wave simulation I mentioned before. Okay. And here, okay, as I said, okay, we can resolve all those wave components to some great details. Okay. So therefore, okay, what is unique in this kind of computer simulation is we can resolve each individual wave components. Okay. Then to examine them in this physical space to have a good understanding about this dynamic system. And here is another example. So what is happening here is there's a current. So we can imagine this is like at river mouth, okay, at estuaries. You have river water coming out of that, okay, and it might enter lake or it might enter ocean, okay, and then to see how that out of this current flow interacts with this ambient flow motions, okay, and then okay, next, okay, give you another example, okay. So this is what is going on at the upper ocean surface or at the upper lake surface. And for this one, okay, that is we can resolve these waves explicitly, as I mentioned. Then we can look at what is the turbulent flows, okay, going on that. And at the later part of this talk, I'm going to talk about the latest problem called Langmuir Cels in more details. And here is one example that shows how powerful computer simulations can be nowadays. And this is an example of teamwork. So we collaborate with two other teams. Okay. One is at the Naval Research Lab. Okay. So then okay, the researchers there, they use really large scale models to simulate what is happening in the west of the Pacific. And then this is South China Sea. Okay. And this is China and this is Philippines. Okay. And in this regime, that is where the internal wave is most active. Okay. So therefore, okay, we can see those kind of wave, okay, propagation, okay, that is due to something happening underwater. And then another team that is at Stanford, led by Professor Oliver Springer, he calculated the simulation at this intermediate scale that is within that black box. So then he can calculate this internal wave. Okay. Then he handed his output to us. Then we focus on what we call fine scale. And fine scale in this case is actually about 1 kilometer, okay, that is 1,000 meters across. Okay. Then to look at what is going on here about the interaction between what is underneath, so this internal wave, and how it interacts with the surface wave. Okay. So that is when you see things at the ocean surface. Okay. And what is interesting is due to their dynamic interaction, okay, then okay, here we can see in this part the surface wave, the water surface becomes much rougher, and behind it, it becomes much smoother. Okay? And this exactly corresponds to what people observed from satellites. Okay? So from satellites using sun imaging, actually in the 70s, already people found that over this internal wave, then they can detect there's one zone that is very bright, and behind it, that is something very dark. That is due to the electronic magnetic signal. When it hits the water surface and when it returns, then the rock surface will give more signal return. Okay, and so this phenomena people observed it several decades ago, and people know the mechanism. Okay, but using computer simulation to dynamically capture this process, this is the first time. Okay, so. And then okay, another example is what I mentioned earlier, is about a simulation of flows over very realistic terrain. So here's one example, okay. And because for a lot of research, especially research at the universities. Those are all we care a lot about academic research. We care about academic values. We look at a lot of canonical problems. Okay? But meanwhile, we really want to solve some real problems. Okay? So therefore, okay, here is one example of such kind of approach. Okay? And here is the West Coast. Okay, and very beautiful. It's Route 1. Okay, and and the terrain is really complex. Okay, so that is like about 3 years ago. Okay, then before the Christmas winter break, then before I took off for vacation or whatever. Okay, I told my postdoc and a student, I said, well, can you simulate this? Okay, yeah. So after I came back from my vacation, okay, then my students told me, done. Okay, that is what they gave to me. Okay, yeah. They said, well, okay, you are interested in this area, so therefore they went to Google Earth. Okay, they grabbed that real terrain topography and put that into the computer simulation, and then okay, to study how when the wind blows over this ocean wave, over these valleys and mountains, to see how the airflow behaves over that. Okay, yeah. So they did that really fast. Okay, and so I was really impressed by their hard work over the winter break. And at that time, we used the data from Google Earth. Okay? And later, someone else told us, well, actually, you can use the data set from NOAA. And that data set is so fine resolution. That is much more fine resolution than our computer model can now handle. Okay, yeah. So therefore, basically, it's not exaggerating to say now we almost can simulate anywhere in the world, okay, about any specific site, okay, about the flow conditions there. And then, okay, this is more about on the engineering side of the applications. So in this setting, we have a flexible plate, and then okay, with the dam, okay, and the water release heater, and this is a typical fluid structure interaction problem. And another more complex fluid structure problem is about wind energy that is happening at the ocean surface to deploy the floating wind turbine, okay, and then okay, to see how the wind energy can be harvested over the ocean. And in deep ocean, then the platform has to be floating at the ocean surface. Okay, so therefore it oscillates under this wave action, and also it is subject to this wind load by itself. Okay, so this is some very complex problem, and the scale of this problem actually is quite large. This is 200 meter high. Okay, I mean the height of the hub is 133 meter. The diameter is 200 meter. Okay. So that is even much larger than the utility scale turbine we have. And so this is the first time such kind of complex engineering system is simulated. And here okay, is another example. It's about the study of fish swimming. Okay. So let's watch. Okay, fish, they are much better engineers than we are. Okay, so they can propel themselves in a much efficient way. Okay, so therefore, okay, what people have always trying to do is to learn from them to see, how can we design, let's say, a submarine or something that can, go much faster and save more fuels by that. Okay, so that's why people are studying that, and we are using computer simulations to do that sort of research. And one last example about simulation tools is about the sprays. That is okay. Well, this is not from simulation. This is from video, from camera. Okay. So when the wave breaks, okay, and then we can see all of some sprays, droplets being generated. Okay, and those actually plays a very important role in Earth interactions, in climate change, in the formation of hurricanes. Okay, and so therefore, okay, recently, okay, we were able to simulate such processes using computers. And those droplets are treated as Lagrangian particles, and their size ranges from 20 microns almost to half a millimeter. Okay, and then okay, we can see when the wave breaks, how they are generated and how they are convected in the air by the wind. Okay. And so based on that, we can study that dynamics. Okay. So therefore, using computers, okay, actually we can choose not to go to do the experiment and to study those a lot of processes in computers. But having said that, okay, well, measurement is extremely important. Lab measurement and field measurement, and nowadays there are a lot of different tools, okay, using satellite imaging, as I mentioned earlier, or using airplanes or drones nowadays, okay, and using the deployment of buoys, okay, on water surface, or using radars mounted on ships, so that's submarine radars. So from different measurement data, okay, the question is, how can we utilize those data to obtain a better understanding of the underlying dynamics? So the vision we have is we use that set of the simulation tools developed in the lab. Okay. Then okay, we try to incorporate all those data okay, to do the very detailed computer simulations about that. And based on that, we can provide detailed description of the whole flow field. And also, by doing that, we can actually help the people doing experiment to improve their measurement techniques. So that is the vision we have. Okay? And here, let me give you one example. So in the line of our work, our kind of simulation, there's one distinguished feature, that is, we always need to collaborate with people doing the measurements, okay? Either in the lab or in the field. Okay? And so here, I give one example about a recent project. So this is on East Coast, okay, North Carolina, okay? And then here's the Atlantic Ocean. Okay? And then okay, we were interested in okay, the flow processes in that regime. So then okay, with working with collaborators, how can I go back? Yeah, it's not responding. Yes, well, that's just okay. So basically, that was so one page really fast. Okay, so in that page, okay, my collaborators they use airplanes, use ships, okay, and go to the ocean to do all those kind of measurements, and then provide that data to us to do the simulation. Okay, and at the end, I will give another example similar to that. So we are not going to lose much. And for the remaining of this talk, I want to focus on one particular problem. That is okay, something we have all seen that at the lake surface, even at the surface of some bigger ponds, and also at the ocean surface. So that is called the Langmuir Cels. So that is okay. Oftentimes we can observe a lot of those long streaks. Those long streaks at the water surface, okay, they are along in the wind directions, okay, and they are made by those kind of floating materials like foams, bubbles, or sometimes even leaves of trees, okay, and then okay, at the lake surface, actually, I'm pretty much sure you can see them a lot, okay. For example, here is actually this is my backyard, okay, and one morning when I woke up, I just saw those kind of long streaks, okay, then I took after my cell phone and recorded that. Okay, and I saw that really, a lot. Okay, for that. So this okay is something okay, people observed for a long time. Okay, and here is another example. Okay, that is what happened in China. Okay, that is in 2008. Okay, that is at the site where the Olympic game was happening at that time. Just because the Olympic game at the well, the sailing, that kind of competition was going to happen, then all of a sudden people saw those kind of thing floating at the surface. Okay, yeah, okay, and in these kind of streaky structures. Okay, yeah, so that scared a lot of people. Okay, and so this okay, well, okay, even was recorded by Darwin. Okay, so in his book, okay, then he wrote, okay, when he was on that voyage of Beagle, and then he said, well, he observed those kind of bands of materials and how long they are, what colors they are. Okay. And what is happening okay, from the fluid mechanics point of view is here. Okay, what is underwater are those very large, very organized vortices, pairs of vortices. Okay, So just imagine this is the lake surface, okay? You have a vortex doing things like this, rotation and motion. Then at the lake surface, due to this vortex rotation motion, they will convective materials converge to this area. So that is where you see those kind of long streaks of bubbles floating materials. Okay, yeah. So therefore, okay, those are caused by those kind of organized structures. Okay. So the question is, okay, well, okay, what caused that? And this phenomena was named after Langmuir. Okay, and the Langmuir, we know, okay, he is a famous chemist and physicist, and he actually won a Nobel Prize in 1932. Okay, and what was interesting is, well, okay, he in 1927, when he was on a trip, okay, going across the Atlantic Ocean, then he observed at the ocean surface, okay, there were those kind of long streaks. Okay, and he actually is someone who actually loves the nature very much. Okay, so when he came back from that trip, okay, and something interesting is, to me, he was a chemist and a physicist. Okay, but meanwhile, he cares about the flows, okay, water flows, especially flows at the lake very much. Okay, so he and his wife, okay, actually often went to the boat and do quite some measurement. Okay, so he did some interesting experiment, and this actually, to me, is almost laughable. Okay, but really, when I thought about that, really that is something quite clever. Okay, so at that time, he used some umbrellas, okay, and to let them to kind of and put some stone in it, adjust this weight of the stone so that they can be floating in the middle of the lake water. Okay, then he did the experiment in ice. Okay, and he worked for GE. Okay, at that time. Okay, so I guess he had no problem getting those bulbs. Okay, and so therefore he used this illumination and to study, their relative motion about that. Okay, and after those studies, okay, then in 1938, he published a paper in Cels, okay, and to describe this phenomenon, okay, and then he argued that was due to the wind, due to the wave, and due to this kind of paired vortices, okay. So therefore, he was the first one, giving this kind of mechanism, and so therefore, for this phenomena, okay, is named after this chemist and physicist. So people call it Langmuir circulation. Okay, and actually that's a very good journal in that area about the surface chemistry. The journal's name is called Langmuir. Okay, yeah. And so this Langmuir cell, it has great impacts on lots of things happening. For example, about climate change. Okay, so as we imagine, for those kind of things happening in the ocean, with or without it, the mixing will be a huge difference. Okay, so here is about what people found about the model. That is, okay, about this mixed layer depth, okay, with considering the Langmuir cells and without considering Langmuir cells, it can be, as large as like 90% of the error. Okay? And this is about the sea surface temperature error. Okay? That is, without considering that phenomena, the sea surface temperature can be like 3.6 degrees different. Okay? So when people talk about global warming and then 3.6 degrees, that is a lot. Okay, yeah, okay. So that is obviously important. And this is about pollution at ocean surface. So this is what happened, several years ago in deep water horizon, okay, in Gulf of Mexico. Then, after that very unfortunate tragedy, then those kind of crude oils are at the ocean surface, and they sometimes don't distribute uniformly. They form those kind of long streaks. Okay, that is due to the Langmuir cells. And so really they have a lot of different patterns depending on a lot of like wave conditions, wind conditions. Okay. So to clean those, we need those knowledge. Now here is about ecosystem. Okay. That is about those paired vortexes. Okay. Then about those phytoplankton. Okay. And they have a tendency, let's say, swimming against that current. Okay. So therefore, those phytoplankton, they will have some preference distribution in the water due to in response to these kind of Langmuir cells. Okay. And here are some observation people saw, okay, that is about algae, okay, that is in North Sea, and they are concentrated, okay, in those kind of, okay, the bed structures. Okay. And here are something harmful, okay, here, okay, near Australia. So therefore, people observed those a lot. So now the question is, what is really the mathematical description for that, and how to describe that scientifically? And here, probability theory was proposed by these two great researchers in the 1970s and 80s. And before that, there were many studies, all kinds of hypotheses about their formations. But this theory turns out to be the most successful theory so far in the 70s. So here, what it shows is, well, here's there's going to be some math involved, but basically the flow, we describe that using vorticity, and then look at the vorticity governed equation. And something interesting is this has to be in a wave environment. So therefore, the flow can be decomposed into the motions associated with the water waves and for the remaining turbulent flows. And based on that time scale, then what their theory says is to decompose these fluid motions according to a different time scale to consider those rapid motions and those slow motions. And then consider them separately, but of course they have certain interactions. And then using perturbation analysis, using some that's quite analytical, then they are able to solve these slow varying motions using this equation. And this equation, the top one is the vorticity equation, and the bottom one looks very much like what we have studied in introductory fluid mechanics course. That is Navier-Stokes equation. So that is constant term, nonlinear convection term, pressure gradient term, and the physics term. So what is new is just this last term. That is called this vortex force term. So that is what their theory eventually says. That is, they said, well, for this wave effect, it can be described by including this extra term in the governing equation. So very simple conclusion eventually. That is what all those great theories are, but very effective. So this theory has been in use very widely. And what I have just described is some mathematical form. Next, let me try to explain this theory using something more direct. Let's see whether this can play out better. So this is about this vorticity equation. So let's look at this physical picture. So previously, we have wind blowing over the lake surface. So therefore, here's the wind direction. And then using the wind shear stress, we have this mean current. We have this current in the lake. So with this mean current, let's see, in the span-wise direction, we have a little bit of perturbation. So in the nature, a lot of things have happened. So things will never be uniform. So it is allowed to have some perturbation. So once it has this perturbation, then we have this vertical vorticity generated. So therefore, we have this kind of vertical rotation, this rotation motion. And then now we have this wave in presence due to this wind action. And what is associated with the wave is what is called this Stokes drift. So basically, when we have a wave, then the materials will be convected in the wind direction, in the wave propagation direction, slowly. So therefore, due to this convection, then this vertical vorticity now is turned into this streamwise direction, into that direction. So eventually, what is happening is they will form that streamwise vorticities, as I mentioned earlier, in pairs by those pairs of different vorticities. So that is the explanation of their theory from this direct physical picture point of view. So their theory has been quite successful, but if one thinks about that, then one can actually find what they capture are some effects, but not all effects. So therefore, another question is, what is the limitation of their theory? And we can see, it is only accounted for those slow motions. And then it is very hard to quantify, to apply that theory in real environment when you have all kinds of different complex wave components. So therefore, it's in the reality, it is a little hard to apply that theory. And also, when we have in shallow waters, in tidals, and or in storm currents, then a lot of assumptions in that theory are violated. And in previous computer simulation study, when we examine them, then we don't find that they are helpful because they are all formulated based on this previous theory. Okay, so therefore they cannot go beyond the theory. So what we do in our study, that is, we just take into account everything. Okay, so we study this by brute force. We simulate everything using supercomputers by brute force. Okay, then by doing that, then we can examine what is the limitation of this theory and what can people do to improve that. So how do we do that using computer simulation? Well, very simple. Okay? We start with some simple setting first. We generate these flows in this computer and to put a wave, put a wind stress to see what happens. Okay? And ideally, we want to capture the formations of those counter-rotating vortices. Okay? And then if we can capture that, then we can study the underlying mechanism. And those are some detailed parameters in the simulation of the skip. So now let's see how we do about that. Well, that is what came out from our computer simulation. Do you see those kind of long streaks? Yeah, okay. So those are the signature of these Langmuir cells. Or we can even see it more clearly from this one. This is the top view of this water surface. So initially, we just put those kind of particles randomly at this water surface. Okay, and statistically, they are uniformly distributed. Okay, so let's start this simulation, then to see what happens. Those are different waves happen. Then, can you see those kind of streaks are formed dynamically, okay, in responding to what is happening in the vorticities underneath it. Okay, so this, to my knowledge, is for the first time such a kind of phenomena, although looks simple, being captured in computer simulations, without theory. Okay, just do it based on Langmuir's simulation. Okay, so that is what we have achieved. Okay? And based on that, we can just go on to study a lot of statistics, turbulence statistics, like what is the mean profile. Okay, and with and without a Langmuir cell, they have huge difference in the current. Okay. And in the turbulence fluctuations, okay, they can be a lot different. Okay. So here, red line is with the Langmuir cells, the blue line is without the Langmuir cells. That's a comparison. Okay. And we can further go on to study this vortex evolution. Okay. And due to time limitation, I'm not going to go to the details of those mathematical analysis. So let me just jump to the conclusion first. Okay. That is, okay, what we observed is really this wave effect, okay, is really important. Earlier I said, well, the explanation of Langmuir, of Craik-Leibovich theory is about those vertical vortex being turned into horizontal direction to form those kind of eventually horizontal counter-rotating vortices. Okay. So therefore, from our direct simulation, we verify this theory. Okay. So therefore, this part is captured. Okay. So that means that theory is a good theory. Okay. Yeah. So but there's something more. That is, okay, we also observed two additional terms contributing to this. That is due to the correlation of the fluctuations. Okay. So therefore, to explain this in a physical picture, that is, there are something fluctuations, okay, but they have a certain correlation. So that there's some lag effect, which also turns this vortex into this streamwise direction. Okay. So that was our finding. Okay. So therefore, there are two things going on. Okay. The previous theory described one thing, but there's another factor which is almost as important, because this half of that, when you add these two halves, then that is almost as important as the other. Okay. So therefore, there's another process going on. Okay. And about another direction of vortices dynamics, I will skip. Okay. And then, okay, another thing I want to mention is about the turbulence kinetic energy. So what it means is like in the upper lakes, in the upper oceans, okay, there are those kind of turbulence fluctuations, which plays a very important role in the mixing of, let's say, chemistry or biological processes. So where do those the energy come from? Okay. Then, okay, what we can see is they come from the wave pumping. So therefore, in this figure, what is shown is about a spectrum and at different frequencies, at the wave frequency and harmonic wave frequencies. So therefore, the periodic motion of the wave keeps pumping the energy into this turbulence field. Okay. So the question is, how large are they? Okay. And we can do the computer simulation as we described, and we can do a lot of analysis about that. And then we skip those details. Okay. final results. So what does this final results tell us? Very interesting. Yes, we find that it's a mean effect, which accounts for 47% of the energy source. But there's another, also due to the fluctuation effect, similar to the vortex dynamics, that is 52.6% in that case. And what does the traditional theory tell us? It tells us there are 47% of that energy. That is very close to this mean effect. So that means actually this theory, actually is a very good theory describing this mean effect. It's so close, very accurate, right? But something is missing, which is huge. There's another half of the energy source actually is missed completely. Okay, yeah. So this is some very exciting finding. One of my PhD students got. Okay, and now what he is working on is to develop his own theory to tell, to explain, to model this effect. Okay, and not as good as this one. Okay, but he told me now he's like 75% can be captured by his model. Okay, but none of us are happy. So he still have some time, years to go about his PhD thesis. Yeah. Okay, yeah. So here's a summary about this kind of mechanism study. That is like using computer simulations. What can we do about evaluating the existing theory, and how can we do to develop a new theory about that? And using the last few minutes, I'm going to tell a little bit something about the work in the field. So, well, as I mentioned, I don't know how to do experiment. I don't know how to do any measurements. Okay, but I do appreciate the value of measurements because I always constantly collaborate with a lot of experimentalists, including my colleagues at SAFL. Okay. So here's one example about this Langmuir cell problem. Okay. It is really such an important problem that lots of research devoted to that. Okay. So about 1 year ago, then in south of LA, and here in Pacific Ocean, there's another big field campaign went on. And here, people deployed, airplanes, boats, and so on and so forth. And here's one of very interesting boat. So I showed the movie here. Okay. So this one, well, looks like there's a vertical tower here. That actually is a boat. Okay. So what it can do is at that location, then half of this tank is filled with water. So therefore, it can turn 90 degrees to become a vertical tower. Okay. And it can stay at this ocean surface for several weeks. Okay. And then people can do all kinds of measurements there. Okay? And after the job is done, then they turn it back and then go back home. Okay? Yeah. So therefore, this is some very interesting facility. Okay? And this research vehicle, well, if we think about that, it needs to turn 90 degrees. Okay? And I have been on it. Okay? So I know it's like for everything, like all the furniture in that boat, it needs to be able to turn 90 degrees. Okay? So this side is the floor, this side is also floor. Okay? Everything. Okay? So you can imagine, including what? Kitchen and the refrigerator, okay. And what I was mostly interested in at that time is to look at, well, how do you guys deal with the toilets? Okay, yeah. Okay. And the toilets, they can also be turned 90 degrees. Okay, so yeah. So that is my colleagues used to do that measurement. And that field campaign was in the spring of 2017. But something interesting is, well, the leader of that campaign, Professor Eric Terry, at the Scripps Institute of Geography, that is at the UCSD. Several weeks before that, in February, he sent me an email. Well, he said, well, we will be sailing on March 15, okay? He said, do you think it's feasible to have draft results, to have a guided deployment of this sampling strategy? Okay, yeah. So that is a little bit scary. Before they have been planning that field measurement for 2 or 3 years. Okay, and before they went to the sea, then all of a sudden they felt cold feet almost. It's like, well, they need some guidance about it, how to deploy their, measurement equipment. Okay, so well, of course, there's only one answer. Yes, we will do that for you. Okay, yeah. So what we did is fortunately before that we already have developed one set of very advanced numerical tools to study flows in the real ocean, very complex wave system. I'm going to skip all the details, and then what is shown here is like one final result. And that is using the realistic wind data, the wave data from the ocean to do the realistic simulation. Okay, And you can see after a while, okay, of the simulation, do you see those kind of round streaks? Okay, so those are the formation of landing cells. So we are able to tell them, here the distance is like 100 meters, okay. So therefore, when you deploy your measurement equipment, they need to be 100 meters apart or something, okay, yeah, okay. So those information we give it to them, okay? And then, okay, well, okay, before they went to that, okay, yeah, then okay, they send us another email, okay, yeah, okay. And so I would like to receive spatial temporal scales from your results to guide our mission planning for our vehicles, okay, yeah, okay. So that looks like, we have done our job, okay. But that again scaled, okay, because this kind of field measurement, involves all kinds of, boats. This is a flip, and this is a research vehicle, Sally Ride. And you probably know Sally Ride was the first woman astronaut going to outer space. Okay, so this was named after her after she passed away, okay, 19 years ago. So therefore, okay, if we rely completely on our computer simulation, so I was thinking, well, should you trust my simulation that much? Okay, what if you mislet them yourselves, right? Okay, then we all point a finger at me. Okay? So I was scared. Okay, and they were at ocean. Okay, so therefore it's not so easy to communicate. Like, have you captured that? Have you seen that? Right? Okay, yeah. But okay, they sent me something, that is on this is on April 6th. Okay, of last year. Okay, that is from a radar. Okay, look at this. Okay, yeah. So those are from the marine radar to show those kind of landing cells. Okay, yeah. So therefore, okay, eventually that was a happy ending. Okay, so they captured that landing cells, and so that was a field successful field. And then after those several years, from starting with last year, then people were busy, analyzing those field data for quite some while. So with that, I better stop here. I'll be happy to answer your questions.
So are you solving an equation that involves conservation of mass?
Yes.
So you have a change in some quantity with time, you get another change in another quantity with distance.
Yes.
Right.
Yeah.
That's very similar to a lot of the equations used in porous media flow.
Oh, okay. Yeah. And those kind of conservation laws are really important. So let me give you one example. So last month, a student of mine, we submit a paper to a Journal of Computational Physics. Okay. So that paper is entirely about the numerical schemes about how to conserve those quantities accurately. Okay. Because previously the code we developed, about 1 decade ago, it was already something most advanced at that time. Okay. But it's not fully conserved in mass and the momentum. So therefore, for this kind of long time evolution of the flow phenomenon, okay, after a long while, then some mass is lost. Okay, some momentum is not accurate. Okay, yeah. So therefore, we needed to treat the numerical schemes very, very accurately. So that student, he formulates everything from scratch again and complete the reload code.
That was like a round-off error or something?
Yeah, and also it has to do with those round-off errors they accumulate. Okay, yeah. So therefore, he designed some schemes to conserve it by construction.
Now that there has been like that field survey that was done with the flip.
Yeah.
What are like some of the next were you missing pieces for field measurement data that you want to see to like really augment your program?
Mm-hmm. Right. Yeah, that's exactly what I wanted to achieve using the last part of my simulation tool part about the data simulation. Although I didn't point out that tool explicitly. Okay, so that is from field measurement. Okay, people can obtain data about this point or about this cross section very accurately, and they have a much better computer than what I have. Okay, I only have the best computer of DoD. Okay, that's it. Okay, but they have Mother Nature as their computer. Okay, so that is more accurate, right? Okay, yeah. But the thing with measurement, I guess you all know that is, it can grab data only at a certain location, at a certain time, certain resolution, right? Okay, so using computer simulation, what we want to achieve is to reconstruct this entire flow field in 3D and give it in time sequence, so therefore 4D data. So data simulations, we want to use the measurement data to constrain our simulation so that at those locations, they are forced to, in agreement with each other, let's say, okay? But for the rest of the domain where people cannot measure, okay, then we will be able to tell them, oh, here's the X, here's the data. Yeah. So that is what I envision, how the computer simulation people can work together with the measurement people together.
A little bit like the atmospheric models.
Yes, yes.
You know, they have these very nice models, but then they're not. I mean, they'll be right for a couple of days, and then they'll kind of go away their own way, and so then they have to bring them back using field measurements.
Exactly.
The atmospheric balloons and other kind of things.
Yeah. Yes. So we learn a lot from them, okay, because they are really advanced in data simulation. So just like a numerical weather forecasting, you know, okay. Meanwhile, you know, at one time they are doing the simulations about the atmospheric flows to predict the weather, you know, 10 days away from now. But meanwhile, there are those stations, you know, keep collecting, meteorology data. Okay, so therefore they can use those meteorology data collected to correct the simulation at the same time. Okay, yeah. Okay. So therefore, using that, this simulation can be more accurate. Okay, so therefore, this is some dynamic system, and in our simulation, the data from measurement can be injected into our simulation from time to time to help correct it. Exactly.
How consistent are mathematical models from the scale that you work at to the scale that the Stanford people work at, to the scale that the people the whole China Sea work at? I mean, you're more mechanistic. What's the sort of representative elementary volume or whatever at which the mechanistic equations apply, and when do you have to make the transition to more empirical equations?
Yeah. Basically, for large scale models like the one they have been using, then they use a lot of more empirical parameterization. Okay? And we focus on more final scales, so therefore we solve a lot of more things from the principles. Okay? But we can only solve things at a smaller domain. So the purpose of that project, that is a NOPA project, National Geography Partnership, or something like that. Okay, and so what they want is to have different models to put them together seamlessly. Okay, and so therefore, what he wants to achieve eventually is from large model. They say, oh, something might be interesting here, but they have reached their limit, so they can not resolve those details. Then they ask the next person, can you resolve that? And then stand to ask us, to further look at the dynamics. Okay. So therefore, in our simulation, we have the input from them. Okay. So therefore, in some sense, our simulation is driven by those large-scale models. So it can be much more physical compared with we just do it alone by ourselves. Okay. So this is one way. Okay. Well, okay, after 3 years of project models, we have achieved that. So therefore, that is no problem. But what about the other way? That is, from our small scale, more physical simulation, can we help them to improve their model? Okay. That we haven't achieved that yet. Okay. That requires another project. Hopefully, they will give it to us. So that is, to learn from our data and how to improve their model.
So models counter turbulence. Turbulence can occur at this scale, this scale. Right?
Yeah.
But your model is actually your representation is
larger than, yeah. So what do we use?
So that's the smallest scale.
Oh, yeah. Okay. Yeah. So what we use is large eddy simulation. Okay. So large eddy simulation, this method, by definition, it simulates large eddies. Okay. So it's kind of large structures. And large is larger than the grid size. Okay. And for smaller eddies, that is smaller than grid size, then we have to use some scale model. Okay. Yeah. So therefore, okay, it still uses models, okay, but the models are at a much smaller scales, and so therefore they are relatively easier to model because turbulence is more isotropic at that scale. Okay. And so our grid size, the smallest one in vertical direction is about 1 meter high. Okay? And so this resolution to people like meteorology people, that is already very, very fine resolution. Okay? Because typically for people look at the flow over lake surface, or for example, okay, what they don't know is what happens like 5 meter, in the 5 meter vicinity of the surface. Okay? That is hard to measure. Okay? Especially in open oceans, it's very hard to put some sensors, close to the surface. And
maybe more umbrellas.
Yeah, umbrellas. Yeah, okay. And here, that page, I couldn't go back. What was using that one? Something very interesting. Actually, it uses an airplane. Okay, the airplane flows maybe like 300 meters above the sea surface. Okay, but it cannot go too close to the surface. Otherwise, something bad will happen. Right? But it tows a measurement equipment, just like a missile, okay? And then it tows, and that one uses a small cable, and it can adjust its height. So that one can be as low as like 10 meters near the surface, okay? And so it tows about that, okay? Yeah. And so therefore, that was used in one of our projects, okay? And the person used that told me that one was originally developed as SBIR, small business, those kind of projects, okay? And to mimic the missile. And for the Navy, so that people can practice shooting down from the battleship. Okay? But that project was not so successful. I don't know why. Okay? But then those people saw that, they said, well, at least we can use that to do scientific measurement. So they put a lot of those equipment into that missile, the model, and then just tow it, and then to do that kind of measurement. Yeah. And another thing in that movie, which is another technology which is really interesting, that was the Hollywood technology. That is, several years ago, that famous movie got the Oscar award. What is it called? Pi and no, about an Indian young guy on a boat with a tiger. Yeah, that one. Okay, yeah. So they developed a technology to put the camera on the boat. So when the boat is rocking, then the platform can keep stationary. Okay. So one of my co-PIs at Notre Dame University hired the same company from Hollywood to install that on their boat and to put the measurement equipment on that. Okay. And later he told me those people are really expensive. I don't know how he can afford getting money out of his grant to pay those people. But so working with those people are really interesting.